Here's number 6 from test 1 review, and I've drawn the picture on the board that goes with it just to show you what I will also provide on the test itself. So the problem says that the region is bounded by x equal to 0, that's the y-axis, by y equals 3x plus 1, that's the slanted line that intercepts at 1, and by x equal to y squared. That's the parabola opening to the right. But I'll give you this picture right here. But you should be able to recognize what the curves are. That the 3x plus 1 is a straight line, and that the curve is a parabola, and that x equal to 0 and x equal to 2 are vertical lines. That lets you know that this is the region, because that's the only part of the picture on the board that's got the boundary described by those 4 equations. Alright, so it asks you to find the volume of this region rotated around the y-axis. I believe that's correct. Let me check. Oh, nope. Rotated around the x-axis. So, let me write that here. Right, so first step though, doesn't matter what it asks you to rotate around, the first step is to decide whether it's type 1 or type 2. So this one is type 1 because vertical slices always have on top slanted line and on bottom curve. Doesn't matter where you make the slice, it has the same top and bottom. Sort of like top and bottom crust on a slice of bread. And horizontal slices fail that. If you try to slice it horizontally, sometimes you've got a vertical line on the right and a slanted line on the left. Sometimes you have a vertical line on the left and a curve on the right. It's never quite the same. Sometimes even a vertical line on both sides. No, that won't quite happen, but definitely all the horizontal slices have different left and right boundaries. We want vertical slices on this one, so type 1. That means we're going to use dx, x1, x2, and functions of x. Now we also need to know, once we've drawn those slices, we need to figure out what it looks like when you rotate them around the x-axis. Well, here's the x-axis. Rotating those slices around the x-axis is going to take the whole slice and spin it around, so it's going to make a washer. It spins it around like end to end. So you could draw the washer right on top of there, or I could put it over to one side or the other. I'll draw it here. So here's what it looks like when that slice rotates around the x-axis. It spins around in a complete circle. Of course, when I draw the circle, it looks like an ellipse. I'm trying to make it sort of 3D or with perspective. All the way back around. Put some thickness. The picture doesn't have to be perfect. Mine isn't either. And that's the center of rotation. That's like the axis it's rotating around. So what we have is a disc, but with the hole cut out of the center. So it's a washer, and the thickness of the disc is dx. So you put dx there if you want. That means that the volume of the disc will be the big circle area minus the small circle area times dx, and dx will go at the end of the integral. So the big circle area will be pi r squared times where the radius is the big radius. So we'll need that. Sometimes I call that R1 or R2. Big radius. The important thing though is to figure out what it is in terms of, since we're doing type 1, in terms of x? Well, that top line is the big radius, and y equals 3x plus 1. So 3x plus 1 will be the top radius, whereas the inside radius, the smaller one, will be the other curve, and that's the y squared. And here we have what? Y squared equals x. We need it to be solved for y so that we have a function of x. And so we need to solve that and just find y equals square root of x. So you could add that here underneath. Therefore, y equals square root of x. This one I'll just use as is, y equals 3x plus 1. All right, so now I have a big radius and a small radius. Pi r squared is the area, so that means that my volume will be, well, x1 and x2. That's clear from the picture and from the given boundaries, x equal to 0 to x equal to 2, smaller to larger. I'm using pi r squared, and I'll be doing it 2 times, so you can just put the pi outside, then do the subtraction. But both of them have to be squared, and that means you square them separately. It's pi times the big radius squared minus pi times the small radius squared. So that'll be 3x plus 1 quantity squared minus square root of x quantity squared dx. That's the setup for the volume. It's a washer setup, which always happens whenever you have a type 1 rotated around a horizontal line, in this case the x-axis. So that will be the answer for several of the questions possibly on the test, where you don't go any further, you just do the setup. But now we could pretty quickly get the final answer. It will be another easy raise and divide, because these will all turn into polynomials. Square root of x squared will turn into just x, because these are positive values, 0 to 2, so we don't have to worry about negative square roots and a square root of a negative. And 3x plus 1 squared, we'll have to FOIL that out. So it'll get 0 to 2. It is quite possible to pull the pi outside of the integral, since it's just a constant multiplier. And inside I'll have 9x squared plus, and you can multiply those 3x plus 1 times 3x plus 1, and you have first, outer, inner, last. It also turns out that you always have the first one squared, since it's 3x plus 1 times 3x plus 1. Then you have twice the product of the two, because you have the inner and the outer are both going to be 3x times 1. So I get 6x and plus 1 and minus x from the square root of x squared. Now I'll let you raise and divide that and plug in the 2 and the 0. Comes out to the total number times pi. Let's see. Since I'm out of space on the board, I'll just look at it here. Comes out to 36 pi. But like I said, this would be an excellent problem to just say set it up, stop with the big box there, so that you don't have to do any more arithmetic on it.